In this demo, we present a compiler pipeline for compilation of convolve use cases using universal flow with RISC-V acceleration for general purpose RISC-V ISA. This pipeline targets RISC-V platforms as used in convolve accelerator. In this demo, we present two approaches. One is the compilation pipeline OML vect, and we also present compiler assisted instruction fusion for generic RISC-V CPUs. Our approach, OML and OML vect, supports compilation for almost all use cases from Work Package 1. We also support models such as CNN, RNN, YOLO, and dynamic neural networks. And we have successfully compiled at least one use case per provider from Work Package 1. And specifically, we support compilation for NSNet2, ConfessNet2, DMARCs from Jabra, and YOLO v6, v7 from VI Notion, and band selection from Thales. Let's take Jabra use case NSNet2 as an example, and let's understand how our OML vect compiler works. First step is to export a pre-trained PyTorch model into ONNX graph, and then we apply our data layout modification pass. On left hand side, we see the matrix multiplication which is unoptimized. On the right hand side, we see the matrix multiplication which is optimized. As you can see, the shape and trans B properties are updated to indicate to the compiler that data layout transformation was applied on this specific node. Next step is to lower this into affine dialect. Here we identify reduction using our OML reduction pass. As you can see here, OML reduction pass identifies 16 reduction operation, whereas MLIR was able to identify 0 reduction operation. Next step is we pass this information to MLIR's auto vectorization pass to successfully auto vectorize it and further lower it to LLVMIR and then generate executable binary. Let's run this binary and see the results. Our baseline is ONNX MLIR manual. OML vect was able to reduce the execution time by 50% compared to our baseline. And ONNX runtime, which is the hand optimized kernel for RISC-V CPU, we are able to match the performance of ONNX runtime using our automatic compiler approach for RISC-V CPUs. Next, we present our results for other wide range of models, including transformer models. OML Vect was able to outperform ONNX MLIR default manual on all models, and on average, we get 59% performance improvements. And on average, we are able to match the performance of ONNX runtime ORT, which contains handwritten manually optimized code. Thank you.
Um, Welcome everyone to Instruction Fusion and AADB demo. We show a compile time instruction fusion optimization tailored for RISC-V hardware backed by our own advanced static analysis that is suitable for convolve use case. So we take the NSNet2, which is a convolve use case, LLVMIR generated from the ONNX MLR framework. We preprocess the LLVMIR by running loop unrolling pass, and we run our fusion pass here. So fusion pass, it does three main things. First is it identifies the fusible memory pairs, and it checks for data dependency to ensure correctness, as well as alias analysis to ensure that the instructions can be safely reordered next to each other. And so but the problem is the alias analysis in the LLVM is not very accurate. To to improve the accuracy of the alias analysis, we integrate state-of-the-art alias analysis and we embed the outcome as the metadata in the code to speed up the compilation time by 6x, in line with Convolve's objective to reduce development time. These are the results from the fusion pass, the instruction reordering pass. So for loads, we could identify 63 load pairs in NSA2 LLVMIR. Two of them failed because of dependency, and we could reorder 61 load pairs together. And for stores, we could reorder all 37 of them. And we compile these assembly files into executable binaries, and we run the binaries to get the performance. So we could see the due to fusion, the execution time got reduced by 37%. Thank you.